All right, guys, talking chemistry today. We're going to be going start with chapter 5 in our Becker Chemistry, Precision and Design. This is page 60, and we're going to talk about gases, section 5.1. But before we get necessarily into 5.1, the kinetic theory of matter, there's a couple of things that our chapter tells us concerning gases that we need to remember, and that is right off the bat. It tells us that the air that we breathe is a homogeneous mixture. And what do we mean by homogeneous mixture? It means there's not different layers. It's all mixed together. And I know maybe we have the mindset or the thought that the mixtures or the air that we breathe is oxygen, because we know our body works off of oxygen. However, there's a lot more in that air than just oxygen, and it's all mixed together homogeneously. And so it's not different layers. It's not just one layer stacked on top of another layer like oil and water, but it's mixed throughout. And then it reminds us that all gases are completely miscible. It doesn't matter what the gas is, but all gases will mix together. It's just the behavior of the gases. The molecules have so much energy. It's just the way they work. And it also reminds us that gases have mass. Now, we don't think often of a gas having mass because typically we can't see it, and a lot of times we can't even feel it. And so we think, boy, why would a gas have mass, or how could it be have maybe more terms weight for us? But we say gases have mass. We just remind ourselves that they are particles, and they are atoms, and they do have some mass, or else they wouldn't have any effect on anything. Also, gases can be readily compressed, our book tells us, because gas molecules are so far apart and they're bouncing off the sides of whatever container they're in, they're bouncing off each other, but we can compress those gases, and that's why maybe when we compress them, there's a lot more pressure. We'll talk about that a little later. And gases expand and contract also with temperature changes, and so we've probably seen that happen. Maybe you've seen experiments where people have taken a balloon that's blown up and maybe dipped it in liquid nitrogen, and that balloon just deflates to nothing because those molecules, those particles of gas, they're just stop moving. And so they're not bouncing off each other. There's no pressure, but when it warms back up quickly, it reinflates because those molecules start bumping against each other again. So just a few basic things that we need to remember. Also, on the top of your page there, in the beginning of the chapter, there's key symbols, excuse me, and abbreviations that we do need to remember. That's going to help you throughout this chapter, because we're probably going to talk about some things that are new to us. Maybe some different terms, some different units, and it's good to have that key there at the beginning of the chapter. So if you run across a unit, or maybe just a letter in a parentheses there that you're not familiar with, go back to the first of the chapter and see if you can find out what it is. Don't just skip it. It'll help us when we get there. Okay, now we're going to talk about 5.1, the kinetic theory of matter today. So it starts off by telling us that solids and liquids expand relatively little as pressure and temperature is increased or decreased. Anything that's solid is very unlikely to expand, or us to notice that it does. However, a gas is very, very affected by pressure and by temperature. We already told you a little bit why. Because the molecules of a gas are just really so far apart. And so temperature and pressure can affect those molecules very readily. And as temperature is increased, molecules move faster and faster and faster, and they bump off each other more, and they bump off the side of the containers more, which gives more pressure. But as pressure or as temperatures decrease, they move more slowly, and they hit each other less or with less energy, and they hit the size of the container also with less energy. Our book also tells us, and it's also good to remember, that it's meaningless to describe a gas as having a certain volume unless pressure and temperature are specified. It says because the relationship of temperature and volume have been described in what's known as gas laws. And we'll get into a lot of gas laws We're going to get eventually into what we call the ideal gas law, and maybe we'll mention that a little bit here in just a little bit. But it's only for ideal situation, not for real gases, not for real situations. But we'll talk about that a little later. So there is what's called the kinetic theory of matter. It's also known as the kinetic molecular theory, and that really, it's the observed behaviors of gases is kind of what those gas laws and those kinetic theories. And we'll get into kinetic theory here in just a little bit, but here are the major assumptions that it tells us. Gas laws are in constant rapid motion. Gas molecules in constant rapid motion. Gas molecules undergo elastic collision. That means they don't lose energy when they collide. So they're bumping each other, and energy is either transferred or it's remains the same depending on the molecules that hit each other. And then the kinetic energy of gas molecule is directly related to temperature. We told you that the higher the temperature, the higher the energy. Gas molecules are very far apart and are negligible in volume compared to the volume of the gas. And what do we mean by that? Whatever container we have, if we have a big balloon or a big blow-up ball here, if it could be massive. And if we took the molecules of the gas, just the molecules, not the space they occupy, we could probably fill that into a tiny, tiny, tiny little space. Also, gas molecules have negligible attraction between them. Matter of fact, they're so energetic that when they hit each other, they're wanting to bounce right off each other and go their own way. So the kinetic theory is literally a moving molecule theory. And that's simply what it is. Kinetics, we understand, is motion. And so the kinetic theory is talking about moving molecules, or just reminding us that molecules are constantly in motion. Those gas molecules just never stop moving, unless we get down to absolute zero on the Kelvin scale. And as far as we know, even as best as we've tried here on Earth, we've never reached absolute zero. We've come really, really close, but we've never reached that. And of course, that absolute zero is just an ideal situation as far as we know. And anyway, a gas that exactly obeys all assumptions and all parts of the kinetic theory is what we said a minute ago, the ideal gas. And with the ideal gas, we have an ideal gas law. It looks a little bit, not a little bit, it looks like this: PV equals nRT. And we'll get to that later on in the book and talk about the ideal gas law. But PV equals nRT is something that's used throughout chemistry and throughout most of your sciences that you're going to take in high school and in college. And so we'll need to get a good working knowledge of that. If you look on page 61, there's a little blue box for concepts in chemistry and the concept of proportionality. And there's one statement in there when we talk about proportionality. It's pretty interesting. But before we get there, it deals with variables. And I have some variables up here. And when we're measuring variables, we're talking about maybe different properties, whether we're talking about pressure, or we're talking about volume, or we're talking about temperature. Then those are going to be either related directly one to another or indirectly one to another. So our book tells us if we wish to study the effect of pressure on gas volume, for example, all other conditions have to be held constant, or we could not unquestionably attribute the observed results to the pressure variables. And that's just another side note when we're dealing with our variables and dealing with the relation that whatever we're going to deal with, especially with gases, we have to consider one of the variables or maybe two of the variables constant, and then work with try to find just the one that we're looking for. Otherwise, we cannot take into account everything that's going on with those gas molecules. And again, I know we keep saying this, but as we build through this, we'll hit some more thoughts about that later on in the book. Well, with our proportionality, we're talking here again with our variables. We have two types of proportionality. There's a direct proportion and then there's an indirect or inverse proportion. Now, direct proportion is simply this, and here's a good illustration of it, direct proportion. C equals KD. Matter of fact, this is one of your application problems for this section. C equals KD is a direct proportion. Now, I want us to notice this, that in every one of these, you're going to see a K. Now, that K is just the constant that's being held at that point as we're studying some other part or some other fraction of that gas, or some other aspect of that gas, whether it may be volume, it may be temperature, it may be pressure, but that K is just the constant that's being held. Okay, so as we look at this, a direct proportion, pretty easily understood, is if this being held constant, if D goes up, what happens to C? Well, think of it this way. Let's think of K as, let's assign it an arbitrary number. Let's say it's 1. If K is 1, and I say D is 2, 1 times 2, what does that make C? Well, it makes C 2. What if I wanted D to go up? Let's say D is now 4. 1 times 4 is 4. So C also went up from 2 to 4. And so the direct proportionality says that if one constant goes up, then the other one also goes up. Direct proportionality. So that's pretty easily understood. If one constant goes up, the other one goes up. Now there's a different proportionality called inverse proportionality. Inverse proportionality says that if one goes up, the other goes down. Now let's look at this right here. In this case, let's say K is, well, I don't know, let's say it's 10. Let's give it just a kind of a number here. Put it right there, 10. And let's say B is 2. Okay, so what is A? A is 10 divided by 2, that's 5, right? Now let's make B go up now. Let's say B is now 5. So, ooh, that's an ugly 5. Let's try that again. B is now 5. 10 divided by 5 is 2. And so you understand, in this proportionality, when B went up, what happened to A? A went down. And so that would be an inverse. But what about this one? We haven't seen it like this before. K is on one side by itself. So how do I figure out whether it's direct or inverse? Well, you have to get what one you're looking for. You have to get whatever you're looking for on one side by itself, everything else on the other. And so I would say P equals K over V. And that looks now a lot like this one, this inverse proportion, because if V goes up, P goes down. So that would be inverse. How about this one right here? Again, I need to rewrite it. Then I would say V equals K times T. Well, that looks a lot like our direct. If T goes up, V goes up. Look here, E equals MK. E equals MK, a lot like our direct. If M goes up and being multiplied, E goes up. What about this one? G equals K over R squared. Well, if R squared goes up, what happens to G? It goes down, so it's an inverse. All right, so that's going to cover real quick the introduction into kinetic or gases and kinetic theory of matter. We want to real quick go over something else here, and that's 5.2 gas pressure. We'll try to be a little quicker with this, but understanding gas pressure, what gas pressure is. Since gas molecules are in constant rapid motion, they have what's called kinetic energy. And kinetic energy is simply given to us by the formula KE, or kinetic energy, equals 1/2 mass times velocity squared. And so a lot of those things, excuse me, these formulas may be new to you, but if you see this formula in your book, highlight it, underline it, write it in your notebook, whatever your teacher, your professor has you do. But you're going to need that formula. That helps us get the kinetic energy of a particular gas or maybe a molecule there that's represented. Now, the kinetic energy talks about the velocity and again the mass there of a particular gas. But there's also another formula that we're going to see and we're going to use in another aspect of gas. It's called pressure. And the volume of the formula, I don't know what happened there. The formula for pressure that we're going to use is its force over area, or unit of area. So force over area, a pretty interesting concept. We know that each individual molecule, when it collides, it doesn't produce a lot of pressure because it's tiny little molecules. We couldn't even put a dot small enough on the board to make it where the size of a molecule. So in any one collision where it hits each other and then hits the side of whatever container that we're talking about, does not, we couldn't really measure, but there's so many little gas molecules that are millions and billions that are hitting the side of this, in this case a balloon, hitting each other, bouncing off, hitting the side of the balloon, and giving us that pressure for whatever area that is. Kind of an amazing thing. I'm sure we've all had maybe some helium balloons in our lifetime. Of course, now it's a little harder to get with a helium shortage, but we've all had those. And just a side note, this is kind of an interesting thing. Have you ever had a balloon, a helium balloon, and had it in your house? And if it's good, it used to be when I was a kid, your helium balloon would stay inflated and stay up for 2 or 3 days maybe after you got it. Now you have it one day, the very next day it's on the floor because the mixture of gases with that helium. But even after that, why is it that, or what happens to that balloon, that gas, and what makes it fall? Well, the helium in and of itself, we know is lighter than air, so it should float, and it doesn't just lose energy and just die. That's not the way helium works. But we don't think of it this way. But if we were to take a small piece and blow up this balloon, we would notice that the sides of this balloon, although it doesn't look like it to us, have tiny little holes in it. And those gas molecules, even those helium molecules, occasionally will make it straight through and not hit on the side where that's red and bounce back in, but will make it through those tiny little holes and leak out of that balloon, whatever that balloon, typical balloon, is made out of. Kind of an interesting thing, the way that gas pressure works. So I'm going to go on down, and that's just a side note, not even in your book, but just a side note there. But go on down a little bit on page 62, and it's going to give us the standard international, the SI unit for pressure. Why do we need that? Because that's what we're talking about right now. We're talking about gas pressure and what gives the gas its pressure. But right now we need to learn a standard unit. We know that our standard unit of length our standard units, period, with our science is meters, liters, and grams that we work with. Anyway, in this course, but the standard unit of pressure is going to be the Pascal. The Pascal. Let me erase this right here. So Pascal, P-A-S-C-A-L, and we say P-A for Pascal. Now we don't always use the Pascal, which we'll see here shortly. But 1 Pascal is a very, very small unit of pressure. It's approximately the pressure that a sheet of paper, let me see if I can grab this. If I had 1 sheet of paper and I laid it on a desk, the pressure that paper lays flat or pushes on that desk with is 1 Pascal. That's not very much. It doesn't exert a lot of pressure, but it does give us a base or a starting point. Now, how do we measure this pressure? If there is pressure from gas, how do we measure? Well, there's a couple different things we use to measure pressure. First off, our book reminds us that there's such a device called a barometer. Now, a barometer typically has been used with mercury, a mercury barometer. Matter of fact, you'll still hear on weather stations people talking about the mercury level, not the mercury level, but the level of mercury, there we go, and talk about the mm's of mercury or how the pressure is falling or raising. And so sometimes they'll say that, sometimes they'll use a different unit called bars. It all depends, and pressure is just kind of weird that way. We can use atmospheres, we can use millimeters of mercury, they can use bars, pascals, torrs. There's just a lot of different things that they can use when we're talking about pressure. But the mercury barometer was invented by Evangelista Torricelli. Kind of an interesting name there, but it's neat how it works. We have an open container with a tube coming out of that. Of course, it's open down in the container, but there's mercury in that container. And there will be levels marked on this tube, and atmospheric pressure pushes down on the open end of this this container here. Oh, by the way, I should have colored this in so we understand that there's going to be a vacuum inside here. There's a vacuum in there. In other words, what it means is it's closed on this side. And so as atmospheric pressure is pushing down on it, then it makes this go up. And so kind of an interesting unit. We won't go into a lot of that. You need to read 5.2 on your own. But the height of the mercury column in a barometer is not constant, but varies with location. Here in Arkansas, we may read a certain mercury level, but if you went up to Denver, Colorado, a mile high, that pressure here would be much less. There wouldn't be as much atmospheric pressure pushing, and so the pressure here would fall. It would go down. And why is that? Because there's not as much air on top. The higher you go, there's not as much air on top of you, and so there's less atmospheric pressure pushing down on you. It may be an easy way to understand that. But also, it could depend on the temperatures and the weather. Fair weather is generally accompanied by high atmospheric pressure, and bad weather by low atmospheric pressure. So the higher the atmospheric pressure, it means we're going to have good weather, nice outside. I say good weather. Some people may like stormy weather. There are those people who do. I like to see it rain. But typically those storms move in with low atmospheric pressure, or those storms follow low atmospheric pressure. All right, so I'm going on the next page. I want to hit something real quick. Pressure units. Now we told you you're going to need to know some units for our pressure. Here are the ones that we need to know. Millimeters of mercury. We already told you why we would do that, because we have this barometer and mercury is inside this barometer and it's marked in millimeters. And so it'll have all these little markings on this tube, and those markings are in millimeters, and we can read how many millimeters are there. And then, for instance, and say this, if we say it's 50 millimeters, and let's say it reaches all the way up to here to 50 millimeters of mercury, that would be, for example, how much pressure, atmospheric pressure, is needed to raise the mercury column up to 50 millimeters. So if somebody says, well, the pressure is at 50 millimeters today, well, they're talking about 50 millimeters of mercury. Going on down, so we talked about, we'll erase that here, millimeters of mercury, or Hg, it's elemental symbol. We talked about Pascal, millimeters of mercury. Now we're going to talk about torr, T-O-R-R. Now where do we get that from? Now remember the Torricelli, who invented the barometer. And so it was named in honor of him. But it's equal to 1 millimeter of mercury. 1 torr is, but precisely defined in terms of the Pascal. So I'm going on down. Standard atmospheric pressure, another one. Standard atmospheric pressure is an ATM. Now, there is a relation with all of these. So we have Pascal, millimeters of mercury, torr, ATM. The millimeters of mercury and torr, we've already told you, are really related. So 1 torr, 1 millimeter of mercury. An atmosphere, however, this equals 760 torr. And so it's kind of something new we don't use, or we may not use these a lot aside from in chemistry, but still good to know and to have. So There's another one even. You say, there's another one. Yeah, there is. Another unit used for atmosphere pressure, our book tells us, it's used mainly in meteorology, is the bar, the B-A-R. And you may hear things like barometric pressure, and that's what we use that bar with. And so what is a bar? A bar is equal to 10 to the 5th Pascal. Okay, so they're related, and there's a relation there, but we don't see them a lot. And then there's, I'm not going to put this on here, but millibars you may use in some calculation. Okay, real quick, our book tells us about another device called a manometer. A manometer is a common laboratory device used to measure the pressure of gas inside a laboratory setting. These right here, although they're poor drawings, these are manometers. There's an open-end manometer and a closed-end manometer. The difference with those manometers, you'll read in your book with it, but this is measured against, if it's open air, it's measured against atmospheric pressure. Okay, so whatever the pressure is in that room, and it makes a difference, the temperature, or whether you're outside, whatever the pressure is there, it's measured against atmospheric pressure, the pressure of whatever gas. Now this squiggly red lines is not a liquid, it's a gas. And then we have a closed end. There's a cap on top of that. Now the closed end is just measured really, if you want to say, against a vacuum, a known vacuum inside there, or inside that that manometer. And so it's, again, just used inside of a laboratory. And you can, again, read those on your, that section on your own. Make sure you grasp an understanding. If you look at page 64 real quick, there's chemistry and action, gas pressure, and milkshakes, or even soda is pretty interesting. I won't read all that to you, but have you ever tried to put a straw on a straw on a straw and stack it up, and eventually try to suck whatever liquid up that straw as long as you could make that straw and you couldn't get it? Well, that's because there's a lot of atmospheric pressure that's keeping you from sucking that liquid up that straw. And you say, well, I've done that before. I've had it really, really, really long, and you can suck it up. Yeah, but there's only so far that you can get that liquid up that straw. And eventually you won't be able to anymore. You say, well, I just don't have enough strength. No, there's just a law that is not going to allow liquid to be sucked up a tube, but only for such a height. And that's why most of, you look at wells nowadays, or even pumps for oil that's being used, they send the pumps down and they push that water up, or they push whatever up that they're looking for, because you can always push, but there's only so much that you can pull up due to atmospheric pressure. And that chemistry in action on page 64 explains that a little bit. Go ahead and do all your examples, your concept reviews will help maybe get a better understanding of that. And if you have any questions about it, let me know, and we'll be glad to answer those.